Okay. I just sent you an email that I meant to attach something with my previous email, but I forgot in the middle there. The email contains two examples of prelim questions from 2000, I think, and 2001. And they're sort of similar. Hold on, I'm not sharing my screen, am I? So I'm recording and there we go. Okay, so the first one is just a kind of a description of a binding reaction and then a series of questions about how you might graph data, how you might collect data, what methods might you use, and then what Van Hoff plots would look like depending upon what the entropy, enthalpy, et cetera is. The pH dependence has to do with plotting the LNK data in terms of pH, which I think we'll be talking about more Tuesday. So that will be a bigger issue. Maybe I've sort of been over this, but we'll talk about it on Tuesday. So that's one example. The next example is similar. It describes some reaction. It describes a drug that binds. It shows what a Van Hoff plot would look like if the data were plotted as a function of 1 over the temperature. And then it asks similar kinds of questions. What is the enthalpy, the entropy, the heat capacity for these data? It's showing you what the slope and intercept are. So you need to know what this equation is. And then in this particular case, it's saying that there's a drug and the drug may bind to this protein, or there's a small molecule that binds to this protein. And maybe it binds to the monomer, maybe it binds to the trimer, maybe it binds to both. How would you sort that out? And what would data look like in various plots? And that's part of the whole issue. What would the data look like? How would you solve that problem? What techniques would you use? Necessarily, this kind of stuff often gets into just knowing functional forms. Okay, so I'm sorry, I've got to move something out of the way. Going to activate a pen. You know, if delta G is equal to minus RT ln K is equal to delta H minus T delta S, then ln K is equal to minus delta H over R times 1 over T plus delta S over R. So when you bring the RT to this side, you get an R and a T. This is what you plot versus the slope, therefore, is minus delta HR. The intercept is delta S over R, etc. So this is what you need to know what a Van Hoff plot looks like. And then you can interpret the slope in terms of a delta H if you know that the slope is minus delta H over R. So you got to correct for the sign and the R value. And then the intercept is the delta S, although what people often do is they just take the ln K value and the delta H value and solve for the delta S, okay? And so that's the kind of thing you would need to know to answer part of this question, okay? How you do the rest of it is part of the discussion, okay? And so maybe these two questions could and should be on the agenda. I could assign it for later, but you guys are all sort of, or a lot of you guys are sort of behind in your homeworks anyway. So if I said to you right here and now, binds to a target peptide, it's possible a peptide binds only to the monomer, only to the trimer, or both. How would you study that? How would you study that? That's a question. It's on the table. How would you study that? Any suggestions? I'm specifically asking just about this part of the question. Possible a peptide binds to monomer, trimer, both. I'm asking for deriving an equation, but just that phenomenon, the peptide only binds to monomer, only binds to trimer. How would you study this? Can you think of a way of studying this? A small protein, 66,000 molecular weight, target peptide, so it's a small peptide, it's only 1,200 molecular weight. How would you study that? Anybody? How would you determine the binding interaction between the peptide and FC66? So part of what you have to do in these kinds of experiments is you have to know that something changes. Okay. What changes? Okay. It's only 1,200. So the molecular weight of a complex is not going to change by very much. So in principle, the molecular weight of the monomer is not going to change very much. The trimer is 3 times bigger than that. So it's 180, 196 KD. All right, 3 times 66. So it's 180, 196, if I'm doing my math right, 198, I'm sorry, 198 KD. How would you do that? You need, maybe there's a spectroscopic change. Maybe there's changes in absorbance, although it's unusual for a protein to change 280 values just because a small peptide binds. Maybe the peptide has a color change. Maybe the peptide doesn't have a color change. That's part of the question. Does the peptide have a color? What we mean by that is, does it have a spectroscopic signal? How do I know what the concentration is? I have to usually have some way of knowing what the concentration is. Okay. And is there a change when you add it? Absorbance is usually one of the last things where you would see a significant change. Maybe the protein undergoes a conformational change you can pick up by CD. Maybe there's a tertiary structure change. Maybe when the protein assembles into a trimer, there's a CD spectral change. Maybe there's a change in fluorescence, and you can pick up a change in fluorescence because the environment of the tryptophanes might be different. And then that environment will be influenced by a peptide that stabilizes the monomer or the trimer. The monomer or the trimer has a different sedimentation coefficient. So maybe there's a change in the sedimentation coefficient with peptide addition. Okay, and so you have a reaction that goes monomer trimer. I'm not telling you anything here about that. You have to sort of bring that to the table. Let's say that the S value of the monomer is 4.4. And let's say that the S value of the trimer is about 8. Okay, remember this end of the 2/3 thing? So it's 3, clear, it's 3 raised to the 2/3 power. So it's about 2 point something times bigger. And the fact that it's not 2.8 times bigger, 2.08, I'm sorry, 2.08 times bigger. So maybe if it's spheres, you would expect it to be 8.8 or 8.9. The fact that it's 8 tells you something about a shape. Maybe there's a shape factor in here. But maybe you could see an equilibrium between a 4s and an 8s species. And then you do the experiment in the presence of the drug, the small molecule, and the reaction shifts, favoring monomer, favoring trimer, or both. And then if it binds to both, then there's no necessary influence of the drug on the reaction. Thoughts, questions? So I've been sort of easy on you in the sense that I haven't sort of had open discussions where I sort of force you to talk. But I think we're getting to a point where you have to start thinking out loud. And you have to have conversations out loud. And you have to be able to think, I've learned this. I have no idea how I think about free energies and enthalpies and entropies and heat capacities, but how could I use that to help me solve a problem, yes or no? I've learned a little bit about CD absorbance and CD and fluorescence. How do I use that to solve a problem? So I'm giving you prelim questions as examples. And so right now, the four of you, I think Lindsay's not here, but the 3 of you out of 4 are failing. Okay, that's supposed to be motivation. Okay, so you need to start thinking about how you solve problems, how you study things that allow you to solve problems. And so that's the example. Here's a perfectly good example that I share with students 20 years ago, where I said, here's a description of the problem. How would you study it? How would you answer questions? Can you tell me what the enthalpy is? Can you tell me what the entropy is? Is there a heat capacity? How about just that? Look at the Van Hoff plot. This is a Van Hoff plot. This is a Van Hoff plot, okay? This is a Van Hoff plot. Is there a heat capacity? Yes or no? What is heat capacity? Yes. And so what does this mean? In regards to this? I went over this, but we didn't do a lot with it. We're going to do more with it in the next couple of weeks because we're discussing papers that use heat capacity. Sorry? So the answer is that this is a straight line. The enthalpy is a slope. Within error, the slope doesn't change from this temperature to this temperature. These are inverse temperatures. And so a little bit 0036, that's 277 degrees out here. Okay, so this is 277 degrees. That's about 4 degrees. And then 1 divided by 0.0032. That's 312 degrees approximately here. 312, 313 degrees Kelvin. Okay, so that's approximately, oh, where'd the 2 go? That's weird. That's approximately what? 50 degrees, is that right? 20, 30, then maybe that's 40 degrees. That's 40, approximately 40 degrees. And this is approximately 4 degrees centigrade. Over this range, the slope is constant. If the slope is constant, there's no heat capacity. It's unusual for there to be no heat capacity, but there can be, or it's so small that you can't measure it. Within error, you can't see the curvature. What we talked about a little bit when we talked about this was that systems that have heat capacities tend to have curvature. And so if the data is curved, then that means that there's a heat capacity. And the curvature can be this way, or the curvature can be this way. And so positive or negative heat capacities tells you something about changes in enthalpies with temperature. Okay, does the enthalpy go up? Does it go down with temperature? And then why it does that is a whole different question. What's changing? Okay. Okay, so this is the kind of thing that we're sort of talking about, that you need to be able to think about these data. You know, I recognize that you're not biophysicists or physical chemists, but here you are, you're in a molecular biophysics class, and I'm teaching you this stuff, and I mean it to be practical, and I need it to be something that you can think about. What changes? How does it change? And what information can you learn from it? And a simple thing like a Van Hoff plot has a lot of information and a lot of implications. What are the changes that are going on that stabilize this protein? And it gives you, notice that in this question, I think I turned it around. The other question, it gave you the sign of the enthalpy and the entropy and the heat capacity, and it asked you to plot the data. This is giving you the plot, and it's asking you to tell me what the enthalpy and the entropy and the heat capacity is. Okay, you can do it both ways. In principle, you should be able to do it both ways. What is the appropriate equation for this plot? What is the sign and magnitude of delta H, delta S, delta CP? Here's the equation.
So in this case, the heat capacity will be 0.
Yes, because there's no curvature. It's a straight line.
Yeah.
The enthalpy doesn't change.
Yeah. Okay.
Okay. In the ITC experiment, which is another potential answer to this kind of stuff. Okay. In the ITC experiments, it measures the enthalpy. And so if you collected data at different temperatures, you would see a change in the enthalpy due to an ITC experiment. Okay, and so you would get a particular sign and magnitude that will not change. It will change, but the change will be linear. Okay, it will change, but it will be a linear change. So that's one way of doing this. And we discussed an example of this when we did the ITC data. Okay. For me, one of the easiest things to do, although CD is certainly a possibility, fluorescence is a possibility. I don't have ITC, but Reed Bishop does, and he's actually going to bring that over here to UMC when he moves over here. I would run a sedimentation experiment in the presence and absence of this drug, this compound. And then I would look at the concentration dependence of S in the presence and absence. I wouldn't necessarily just one experiment. I would run a family of samples, different concentrations to watch the assembly. And that would give me the ability to measure the equilibrium constant, depending on how strong the affinity was. And then I would add the drug and repeat the concentration series and ask, do I make more trimer? Do I make less trimer? Okay.
And how do we know that peptide binds only to monomer, trimer, both in this case?
That's the question. That's the question.
Homework.
I'm not giving you the answer. How would you know that? If it stabilizes the trimer, it binds to the trimer. If it destabilizes the trimer, then it must bind to something that inhibits trimer formation. Okay. And so is it simply binding at the interface and breaking up, or is it binding exclusively to the monomer in some way that prevents the trimer interface from forming? Okay, potentially that's a sort of a nuance in the way the question is asked, but that would be the answer. It inhibits, yes or no. We didn't talk about size exclusion chromatography. You could, where is it? There we go. Size exclusion chromatography. But if you ran this protein over a column in the presence and absence of the drug or the compound, would it migrate as a monomer or as a trimer? And could you tell that from the SEC? SEC is not necessarily, well, some people would say it's easier because you can run an SEC column in minutes. And so in principle, you could add the drug and then immediately get the outcome as you have, I can't write over there, or maybe I can write over there. You would immediately get an outcome where the volume and the trimer would come out maybe, it doesn't want to hold it there. Look at that. The trimer would come out first, or the monomer would come out second. And then in the presence of drug, this peak would shift one way or the other. It would shift towards trimer or it would shift towards monomer, telling you that it favored the monomer or the trimer. And so that's another potential way of doing this. A lot of people have automated SEC columns set up so they can watch reactions shift. It's a little complicated by SEC because SEC causes a lot of dilution of the sample as opposed to sedimentation. You could do this by DLS because you would see the diffusion coefficient of the monomer and the trimer. They would not be dramatically different, but they would be different, and you could actually watch that shift in the presence of the drug. That may be a tighter experiment. Instead of going from 4 to 8, the diffusion coefficient might go from, I'm guessing numbers here, it might go from 7 Fic, because it's an increase in molecular weight, the diffusion coefficient goes down. So it might go from, goodness, 7 Fic down to 5 Fic or something. So you would see a decrease in the diffusion coefficient with this same kind of experiment. That would be a relatively easy experiment to do, although it wouldn't be as sensitive. Okay. So I'm going to do that. It's going to actually save that writing. Okay. I think I've already told you that not all of you have turned in 6. Some of you had turned in 2 using this 4/3 pi r cubed. So you'll be, I can return these to you. I was waiting for other people, but I guess it's time for me to return these to the people who have already turned this in. I think 6 is the other one that is giving people trouble because they're coming up with funny numbers for 6. And so something needs to be redone for number 6 for the 3 students who have turned in their homework. I think none of you are sort of coming up with a No, that's not true. I think a couple of you are coming up with one, maybe only one of you is coming up with a funny answer. So basically, I think that's okay. So let's close that and let's go to what else we need to talk about. We need to talk about.
I'm sorry, Dr. Correa. I had a quick question about
Sure.
6.
Sure, go ahead.
The question that you gave us on 6 at the end, you asked, are these two models where P is a function of T or V, are they exact differentials or perfect differentials?
Mm-hmm.
Is that supposed to be exact differentials or partial, or is perfect what you intended? Because I was having a hard time.
The terminology exact differential or perfect differentials are substitutes. It's expressing the same thing. So what it means is if you take the derivative of RT over V with respect to temperature,
Mhm.
but then you also take the derivative with respect to volume, is that equal to the partial of RT over V with respect to volume, where you first or second take the differential with respect to temperature? Is this the same? Does the order of the differentiation matter? Yes or no? And if you get exactly the same answer, then it's an exact differential, or what sometimes some books call perfect differential. So it's
Okay.
just nomenclature.
Okay.
And this is the math that you're doing. You're taking this order, the derivative with respect to T, the derivative with respect to V, or the derivative with respect to V, the derivative with respect to T. Does it matter what order you do it in, yes or no?
Okay, thank you.
Okay. And the same for the other form, which involves the volume, which involves accounting for the volume of the molecules. And I'm going blank at the moment what that equation is called. It has a name. Okay. I'm going to save that. And so some of you have turned in 7. Last week we discussed part of 7 because somebody asked me about it. Okay, and so I think I wrote this on the screen showing you where you can get one equilibrium constant from a combination of the others. So 1,4 is actually the product of 1,2 squared times 2,4. As I say, I have some of the homeworks. I don't think I've actually graded them again because I'm waiting for more of them to come in. Do we have any, I don't think we've discussed this, have we, at all? Well, we discussed that, but what else have we not discussed? Because I think some of you have turned it in. So do I really only have, I have Ahmed's and Jelena and Lindsay's. So I have 3 of them and I'm waiting on the rest of you. Do we have any questions at this point? Do we have any comments? I haven't given feedback yet. I could give feedback. I'll give feedback before class Tuesday now. Are we making any progress?
Dr. Correa,
Yeah,
I think I emailed you my 7th assignment.
you did?
Yeah, I was in the email with, I sent like 6 or 5, 6, and 7 all together. And I had a few that, like there was
Okay.
one question from 7 that I hadn't done, but I went ahead and turned it in.
Yeah,
anyway.
I'll go looking for it. I just didn't probably copy paste it into that directory. I'll go looking for it.
Okay.
All right, and so if I have 4 7s, then I'll make an effort to turn all of, to grade those and start to talk about that next time. Comments? More questions? We're not ready yet.
Yeah, I might have comments on this after I see the graded.
Okay,
Yeah.
let me grade it, and it'll be in your mailbox by Monday.
Okay, yeah.
I may be able to finish it this afternoon. I have another meeting this afternoon, so that may not happen. And tomorrow, I think I'm moving some stuff around, so I may not. I'm having to empty an office, so I may not be able to finish it tomorrow. We'll see. I'll try, but I'll have them returned in your mailboxes by Monday.
Yeah, I'll have questions for you probably next week because there's few questions, 15.7 from this one. And then I have got one more question to work with for assignment 8. So I'll have questions for you next week probably, yeah. And I'm also working on assignment 9 and 10. So there's gonna be a bunch of questions.
You've turned in your 8.
Yeah, I've turned in mine. I've not turned in one question from assignment 8. I'm still working on that.
So we have some absorbance and some CD, and then I have this light scattering correction.
Yeah, I'm working on that 6, the extra light scattering. And I feel like I'm a little bit struggling with that question, but I don't have definite way to ask you as of now. So I'll try to work this weekend and I will let you know.
Okay. More questions? So without looking at people's answers, no, that's not it. It must be well, this question here was the light scattering question, and what I gave you was absorbance data
Yeah.
versus wavelength. Okay, so there's some kind of spectra that has a peak at 280. It may not look like that. What does it look like? I don't remember what it looks like. I have to plot it. Oh, no. Goodness. Erase. There we go. Okay. And so it may look something like this. And then there's something out here where there's some scattering. And what you have to do is you have to plot this as log, natural log, or wavelength. This part of the curve will look a little funky because you're taking the logarithm where you have an absorption band. But this part of the curve out here will, in principle, give you a straight line. And the straight line will give you the wavelength dependence of the wavelength dependence, okay? And so if it's Debye scattering, then n equals 4. If it's microtubules, then n will be equal to about 3.3, but in the 3s. If it's what's called Mie scattering, n will be 2. This particular case, it's aggregates of this protein, it's aggregates of ELP, and so there'll be some slope. And so that's basically what you have to do. The hard part is then once you fit, you don't fit the part of the data that has this, you only fit this part of the data, maybe higher than 350 or so. All right, and then you have to convert this slope, this data, back to absorbance scale. You have to convert the data by taking some inverse way of plotting the data and subtracting it from these data. And when you do that, these data will come down and it'll come down to 0. And the light scattering will suddenly be gone. That's the whole idea. So this absorbance value is wrong, quote unquote, in error by whatever the wavelength correction is. And so this is the easy part, and then fitting just the above 350 or so. But then you have to convert this back somehow to a linear scale. So this curve back to a linear scale where you've corrected basically for the n factor, and you then subtract that from this curve, and it will bring this down to the baseline. It's not that hard. You just have to sort of know how to do it, or figure out a way how to do it, because this is on a log scale, and I'm doing this as natural logs. You could get away with doing this as logs. It's just a factor of 2.303. You just have to convert using 10 to the something instead of e to the something to convert it back. Otherwise, the slope should be the same because both of these differ by 2.303. Whatever he does in the paper, whatever they do in Shiraga's paper, Leach and Shiraga. Okay. If you're struggling with that, I'm going to say save that. What were we? No, I don't have anything written there. What is that? That's not it. Is that? No. So where's the other one that I'm thinking about? How about this question? The one at the bottom. The origin of the term Southern . Anybody?
I'm working on it, Dr. Korea.
Anybody?
So what do you mean by like origin of the name itself? Or Southern is for DNA, Northern is for RNA?
Yeah, but I want to know where the name came from.
Okay.
Dr. Correa,
Yeah.
I may be wrong, but I think Southern was the actual name of the guy who came up with that one, and then the other two were just based off of the first one.
And that's exactly correct.
Yeah.
And the answer to that came only if you read the history of electrophoresis papers I gave you. And you realize that the first article was written by some guy named Southern. And so he wanted it to be called, what does it say? It became blotting, but he wanted it to be called some kind of a transfer protocol. But because it was being passed around in the literature, passed around in the community ahead of time, it became known as the Southern. And then the guys who created the RNA blotting as opposed to DNA blotting thought it would be funny to call it a Northern. And then once we had a Southern and a Northern, it was only logical that we were going to have a Western. Exactly. See, science is actually very funny. Or at least we like to think we have a sense of humor. And often what happens is things have names and we forget they sometimes mean something. They have some kind of a mnemonic device. The letters actually stand for something, and sometimes it's just something that people called it, and other people then try to rename it. And that often is what happens too, that people try to rename it as though they've created something new, when in fact they haven't really created anything new. They're just trying to name it after themselves or something. What else? So I think the prelim question issues that I'm bringing up for you, especially in the context of interpreting thermodynamic data, a lot of that will get answered as we discuss papers in the next 3 weeks, because those papers, part of why I present them to you, I ask you to read them, is because they make Van Hoff plots and they interpret the data, because they talk about enthalpies and entropies and heat capacities. And so it gives you a way of seeing how it's been applied. Okay, and that will be true for the next 3 weeks. The third week, we're doing this drug binding summary from John Ladbury's group, and it's a summary of a lot of enthalpy entropy data, and that will explicitly talk about all of these concepts. Okay, so I'll be reinforcing this a lot while we do this. Questions, feedback? I know I'm not spoon feeding you, or at least I'm trying not to spoon feed you. I know I'm being difficult. But that's part of the whole idea. Okay, I think we're going to stop, and I'm going to see you on Tuesday. You should be prepared, because on Tuesday, I'm going to start to be a little even more aggressive than I've tried to do today. I don't think I've been all that aggressive because I'm letting you get away with it. But Tuesday, you're going to have to do some more talking. I want to hear your understanding, your opinions, your insights. Okay. 2 centrifuge papers and my follow-up paper. 30 years later, 75 and 2004, I think was our paper. Okay.
Okay, Dr. Goria.
So I'm going to stop sharing. And I'm going to, I have to end, I think, to make it stop.
Yeah.